Here we go for what we did Tuesday. All right, we're moving into sampling distributions, and we're leaving behind much of the probability that we covered. I mean, there's AP exam, final exam, and there's a little bit of use for it as we move forward, but the pure probability is pretty much over. So we're going to move into sampling distributions, and what you probably ought to do is look at the first video, which is a decisions through data about sampling distributions. I think it's corny and terrible, but very instructive at the same time. So if you didn't see it during class, or if you slept through it during class, then you can watch it. All right, but we're just going to start out with some terms, and this is kind of a repeat of what we had done much earlier in the year. We defined parameter. This is a number or some value that describes a population. Remember, populations are usually big, and that means that we typically don't know, what these parameters are, like the true height for women in the US, or the I don't know, anything that we would have to measure for a large group is usually something we just can't physically do, right? So rather than just abandon this search of knowledge, because we really do gain knowledge by knowing parameters, rather than just abandon it because it's too hard to do, we're going to go after it through sampling. And when you generate numbers through sampling, then that's going to produce statistics. Now, the issue with statistics, as we have seen, is that when you get numbers from samples, no two samples are typically alike. So, and if both samples are actually giving you, or either one of the two give you an exact value to match the parameter, that's probably really unusual, right? So, the best we can do is to use statistics to estimate our unknown parameter, because of that issue of sampling variation. And this is just what you get, if you're measuring heights of people, you might just pick randomly a bunch of tall ones, or randomly a bunch of short ones. Not a good mix. So due to random chance, results from samples will vary, and it might seem that would restrict our ability to use statistics to estimate parameters, but yeah, it's down to a pretty tight science now, and I have a feeling that you will see later on that sampling variability will be something we can handle. All right, but remember, there's always error in sampling, and error doesn't necessarily mean mistake. It's just a different way to say variability. All right, so suppose that 25% of all U.S. adults are either single or divorced. See that word all right there? Yeah, anytime you see that, or if it's implied, then that value is a parameter. So 0.25 is a parameter because it is a single number that describes all U.S. adults, all of them. So there's no variation in it. There's just one value that you get if it's a parameter. If, however, you take random samples of 50 U.S. adults, let's say 5 of them, and you want to check those 5 to get a proportion for people who are either divorced or single, the results could be like this. And you notice we're using these to estimate the parameter. None of them is 0.25. Oh well, but they all are around them. Now, if we could do this sampling indefinitely to get these statistics, then we could average them up as we get more and more. Then that average proportion should approach 0.25, just like the law of large numbers. But, when you only deal with a few samples, the variability can be kind of big. All right, so these are the values, and they're varying around the parameter. Okay, so for notations, we use mu for parameters. Remember, the parameter is exactly what exists in the population. So for means, if we know the mean for the population, we're going to call it mu. There are a lot of other things that we call mu. Remember random variables, the expected value was mu. Well, that's what we use for definite averages, right? Greek letters. So, an expected value is an exact number, doesn't vary. When it applies to random variables, it's the same if it's a parameter or a mean for a population. X bar is just a number that we get from sampling. It's a statistic. For proportions, we use capital P as the true proportion in a population. That's the parameter. And we use P hat as a designation for proportions we get from samples or for statistics. Now your book may use pi. I know earlier versions did. I'll have to peek back in the book and see, but we're using capital P. All right, so what about this sampling variability? Well, what happens is that if we take a large number of samples of the same size, they have to be the same size, so n may be 35 or whatever, and we do sampling of size 35 a whole lot of times, we're going to get whatever statistic we want, whether it's X bar or P hat, whatever. Let's just say X bar. And we would make a histogram of these values, so they become your data. So it's not individuals that we record data from. Yes, ultimately we do, but we then group them into samples of a certain size and get the statistic out of it. Right? And then we get a whole bunch of those statistics, and then they behave like when we used to get individual data points. So we make a histogram out of it. Check it out, center, unusual characteristics, shape, and spread. Remember CUS. Now, if you could do this process instead of like a large number like 150 or 500, but if we could just do this indefinitely, an infinite amount of times, that kind of jaggedy histogram would smooth out to a smooth curve sampling distribution. It would contain all possible samples of whatever size we're dealing with, and that's what we use for a sampling distribution. It's ideal, so we don't build it. See, this is the theory, we're not building them, but we will understand how they work and the nature of them and how to, do meaningful inference out of them. Okay? So that's what a sampling distribution is. Here's the formal definition. So your sampling distribution, remember we've been working with population distributions, all possible readings from each individual, right? But a sampling distribution of a statistic is the probability distribution of values. Maybe it's means, X bar, maybe it's proportions, P hats, or something else, taken by the statistic in all possible samples of the same size from the same population. All right? So if you watch the video, you can see the plant that makes circuit boards for AT&T, and as they go through the production process, they grab 5 boards at random, and they get an average of a quality rating. And then they do another 5, and another 5, and another 5, and another 5, and get a whole bunch of these averages for quality ratings. And then they build a distribution that, is comprised of those X bar values from all samples of size 5, right? And then they can use the theoretical sampling distribution for means for samples, all samples of size 5, in order to, make some quality adjustments. So we are going to work with sampling distributions for X bar, for sample means, or we'll work with sampling distributions of P hat, which is sample proportions. Later we'll add on more. All right, so for homework, and I don't have my key right in front of me now, but that was what we did last night. That was the night of the test. You had 8 people, and they were members of a board for something, and that was your population because there were no other members of the board, right? So those 8 people constituted the population of people on the board. And they took measurements of how many kids they had. Some had 2, one had 3, some had 0. And you could add them all up and divide by 8 to get mu, because that would be the definite average for all 8 of those people for the number of kids that they have. And it was, I think, 1.375 kids was the parameter, the mu. Well, if you paired those people up, you got 24 distinct pairs. And if you added their kids together and divided by 2, you had 24 unique little X bar values, which represented all possible samples of size 2 from that group of 8. If you averaged all of them, guess what mu sub X bar was? It was 1.375, exactly like the population distribution. Now that population was not normal. Maybe it was not enough members to make a normal curve, really. So this idea works for any type of sampling distribution, all right? So the mean of the population was the same as the mean of all the samples. That's the idea behind sampling distribution. Okay, so you kind of get the idea about sampling distribution. Now bias, I have brought up this word bias a number of times in the past, and I said we would be dealing with it all throughout the course, so it's back. Bias, if something is biased, you may remember my easy way to remember it was to say that it's something that misses the mark, right? It's just off. And it concerns point estimates, so we're talking about the center of the distribution. So it could be mu X bar, mu p hat, whatever, all right? So a statistic is unbiased if the mean of your sampling distribution, all those little sample averages, is equal to the mean of the population. Also, if you have a sampling distribution made up of proportion values, the average of all of them should equal the true proportion for the population. If these are true, your statistic is unbiased, so there isn't any missing the mark when you have these relationships. So if you look at a sampling distribution, the mean of it is going to be equal to the mean of the population, all right? So if you know the mean of the population, you automatically know the mean of a sampling distribution, all right? So in other words, sampling distribution's mean is equal to the true mean of the parameter for all possible samples of a given size. Neat. All right, variability of a statistic. This is going to show up as the spread in your sampling distribution. It'll be measured by sigma sub x bar, and there'll be formulas for that well, they were in the decisions through data film if you watched it, but there will be one we'll reveal tomorrow. But this is going to be determined quite a lot by sample size. All right, the bigger the sample, the tighter it is in your sampling distribution, because bigger samples are more accurate. There's going to be less variability in them, so that just translates to less spread in your sampling distribution. So that's a key thing that determines the spread in your sampling distribution. Now the sampling design can affect it too, because remember, if you're good and tight with how you design a sample and how you do the process, then you don't really bring in that much extra variation. But if you're sloppy with it, you can bring in a lot of extra variation, and that can affect the spread. Remember I said larger samples produce less variation? So think about if you have a small sample and one weirdly small observation or weirdly big one, the average will be affected by that weird one. But if you have a sample of size 100 and one weird one, then those other 99 will help average out the extra variation in it. So that's why larger samples produce less variation. All right, this is a kind of a strange one. For identical sample size, as long as the population is at least 10 times the sample size, variability will not be affected by the size of the population. All right, this is a pretty intense math issue that's in this little bulleted point. And the best thing I can tell you is that the population being 10 times the sample size is important for inference. We're going to be checking that when we do inference later on. And it has to do with the relationships that form your sampling standard deviation, the sigma sub x bar of your sampling distribution. If your population is small, or if your sample size is big enough to start getting close to the population, then you start losing some key relationships that we need in order to do inference. So you can have a fairly big sample size. And remember, big sample sizes start around 30, n is 30. But your population has to be a lot bigger for all of these stats things we're going to do to work. So just file that away. We'll deal with it later. So this, I think, is the last thing. Remember, bias is hitting the mark. Variability is spread. If you picture the bullseye here, 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 and here to be the parameter, and we're trying to hit that with our sampling, clearly this would be the best option because you have low bias. You know, all these points are right about where they should be, and they're not really spread out too much. So this is what you hope your sampling will provide for you, right? The next best thing would be this one. I know that it's pretty spread out, but if you look at it, all these points sort of point into a common center where the true value of the proportion is. It's just, you don't feel quite as comfortable with the spread here, but yeah. Now, probably the worst one is this because it's high bias, but the low variability make you think, oh, they all landed in the same spot. That's got to be where the parameter is. But really, that's kind of a trick. You're far away from it, and so you could be fooled by that. And then this is just kind of a mess. But for me, statistically, letter A would be kind of the worst of all worlds because it tricks you into thinking things are great when in fact your bias puts you way off the mark. Okay? All right, so that's all that we covered today. Worksheet number 1 is really pretty much identifying statistics and parameters within word problems. It's eight problems. I think there's one different one, but that's basically what the other 7 are. And the answers are posted, and tomorrow we will get a little more mathy. All right? So on that note, I'm going to close this out and post it, and we will suspend until tomorrow.